Imagine holding a complex design in your mind, hitting print, and watching as a physical object emerges, layer by intricate layer, right before your eyes. It sounds like something straight out of a futuristic movie, doesn't it?
Yeah.
But here's the surprising part. This technology, what we now call 3D printing or additive manufacturing, isn't some brand new sci-fi fantasy. Its earliest concepts actually stretch all the way back to the 1940s.
It's true. And today, we're embarking on a deep dive into the world of 3D printing. We're going to unpack its truly fascinating evolution, from those visionary early ideas to its current widespread applications across almost every industry you can imagine. You'll discover the incredible variety of materials and processes it uses, and by the end, you'll see why this technology is so much more than just, a niche industrial process.
That's our mission today, to give you a clear, comprehensive understanding of this transformative technology. We want to deliver those aha moments and surprising facts without overwhelming you with technical jargon. You'll learn how it works, its immense practical benefits, and its profound social and environmental impacts. You'll understand why it's changing everything from how we make food to how we think about intellectual property. So are you ready to unpack this?
Let's start with the basics. When we talk about 3D printing or additive manufacturing, what are we actually saying? We're referring to the construction of a three-dimensional object from a digital blueprint, usually a CAD model. The key is how it builds. By adding material, whether that's plastics, liquids, or powders, typically layer by layer, all under precise computer control.
Okay, adding layer by layer. But what's interesting is that when this technology first emerged in the 1980s, it wasn't even called 3D printing. What was its primary use back then? What did people call it?
Good question. Initially, it was mainly used for creating functional or aesthetic prototypes. And the term of choice back then was rapid prototyping. The focus was really on quickly bringing a digital design into the physical world to test it out.
Rapid prototyping. Got it. And then the terminology itself started to shift.
Absolutely. In the 2000s, additive manufacturing, or AM, gained a lot of traction, particularly in metalworking and the production of final end-use parts. This term really emphasized the process of adding material, which offered a stark contrast to subtractive manufacturing.
Right, that's the traditional way, like machining.
Exactly. Subtractive manufacturing became kind of a retronym, a term coined after the fact, to describe those traditional processes where you remove material to create a shape.
So fast forward to the early 2010s, and 3D printing and additive manufacturing became almost interchangeable umbrella terms for most people. But were there still distinctions in how they were used, maybe more professionally?
Definitely. 3D printing often got associated with the lower-cost, more consumer-focused machines that were starting to appear, while AM remained the more formal term, preferred by industrial producers and standards organizations. And while they're often used synonymously in casual conversation, some manufacturing experts still view AM as a broader concept. They see it as encompassing 3D printing plus other aspects of the overall manufacturing process.
Okay, so there's still some nuance there.
But here's the real game changer, regardless of the term you use. This technology can produce incredibly complex shapes, geometries that would be otherwise basically impossible, or at least infeasible, to construct using traditional methods.
Like what? Give me an example of something that's just, impossible without it.
Okay, think about creating hollow parts with really intricate internal structures, like a honeycomb-like truss inside an object. With traditional methods, machining that out of a solid block, that would be incredibly difficult, if not impossible. But with 3D printing, you can essentially grow these internal geometries layer by layer, which significantly reduces the weight of the part and minimizes material waste. It's a complete rethinking of design possibilities.
That's a huge advantage.
Yeah.
And if you're wondering which type of 3D printing you're most likely to encounter today, as of 2020, the most common process is fused deposition modeling, or FDM. That's the one that works by extruding a continuous filament of thermoplastic material, building up the object layer by layer.
Yeah, that's the one most people picture, I think, the filament-based printers.
Now let's go back in time, because the history here is way longer and more intriguing than many might imagine. The early seeds of this concept were sown surprisingly early, not in a lab, but actually in the pages of science fiction.
Indeed. It's pretty cool, actually. Murray Leinster's 1945 short story, Things Pass By, described a constructor machine. It made drawings in the air with hardening plastic. Sounds familiar, right? And then Raymond F. Jones's 1950 story, Tools of the Trade, mentioned something he called a molecular spray. These were truly visionary ideas, especially when you think about what computers were like back then. Barely a concept.
Right, so the ideas were out there in fiction. But they didn't stay fictional for long. In 1971, Johannes F. Gottwald secured a patent for what he called the liquid metal recorder. That sounds like the real deal. What was it?
It was essentially a continuous inkjet device, but for metal, and it's considered by many to be the first patent describing 3D printing with rapid prototyping in mind. And his goal was incredibly forward-thinking for the time. He wanted to minimize material use and even allow for salvaging materials for reuse. So even back then, there was an awareness of efficiency and sustainability.
That's fascinating. And the concept was popping up elsewhere, too.
Yeah, David E. H. Jones laid out the concept more broadly in a 1974 New Scientist column. It shows the idea was circulating among innovators, not just in one person's head.
Okay, so the seeds were planted in the 40s, 50s, and 70s. But the true birth of modern additive manufacturing really kicked off in the 1980s. Were there many different people or groups trying to crack this code then?
Absolutely. It was kind of a race, in a way. In Japan, Hideo Kodama invented additive methods for plastic models using photo-hardening polymers back in 1980. He even filed a patent for his XYZ plotter in 1981. But here's an aha moment about innovation. His project got shut down. Why? Lack of interest and a tiny budget. We're talking $545 a year.
Wow, $545 a year for potentially revolutionary tech.
It's wild, and it's fascinating how many groundbreaking ideas in the 80s were dismissed by companies as lacking business perspective, ideas that, later became billion-dollar industries.
It really speaks to the long gestation period of truly disruptive technologies, doesn't it? Sometimes the infrastructure, the market, or even just the collective imagination isn't ready yet. Meanwhile, in the U.S., others were also making strides. Raytheon got a patent in '82 for depositing powdered metal with a laser. And in '84, Bill Masters filed the first U.S. 3D printing patent for a computer-automated manufacturing process.
And you won't believe this in France. Inventors also filed a patent for stereolithography that same year, 1984. But again, it was abandoned by companies due to lack of business perspective, that recurring theme.
Unbelievable. But then came the person really credited with the breakthrough for the modern era, Charles Chuck Hull. His company, 3D Systems, filed its own patent in 1984, defining stereolithography, using UV light to cure photopolymers. What made his contribution so significant?
Hull's impact was just immense. He didn't just define the process, he also created the STL file format. That's the standard file type we still use. And he developed those critical digital slicing and infill strategies. You know how the machine builds the inside of the part. 3D Systems then released the first commercial 3D printer, the SLA-1, in 1987 or maybe 88. That was a pivotal moment.
Okay, so Hull and 3D Systems with stereolithography, and then another major player emerged soon after.
Right. S. Scott Crump of Stratasys developed fused deposition modeling, or FDM, in 1988. That's the filament extrusion method we talked about earlier. Stratasys marketed its first FDM machine in 1992. So you had these two major players really solidifying the core technologies in the late 80s.
But at this point, were these machines even remotely accessible? Like, could a small business or an individual even dream of owning one?
Oh, not at all. Not even close. To put that in perspective, owning a 3D printer back in the 1980s would set you back upwards of $300,000, which, if you adjust for inflation, is something like $650,000 in today's money.
Whoa. Okay, so strictly for large corporations and very well-funded research labs then.
Exactly.
So moving into the 1990s and through the 2000s, we saw a significant expansion and a gradual move towards accessibility. The 90s brought us metal printing processes, right? Like sintering and melting powders.
Yeah, things like selective laser sintering, SLS. It showed that tech wasn't just limited to plastics, and new material deposition techniques also emerged, like microcasting and sprayed materials. Interestingly, the actual term 3D printing itself originally referred specifically to a powder bed process developed at MIT in 1993. That one used inkjet print heads, kind of like your desktop paper printer, but with powder and binder.
Huh. So the term had a more specific origin. But for much of the early 2000s, these printers were still pretty niche.
Very much so. Still largely confined to big manufacturing and research labs, mostly used for low-accuracy modeling in fields like architecture and medicine, mainly because they were still so expensive.
So how did this niche, expensive technology start to become more democratic? What was the turning point that really began to open it up?
That came largely, I'd say, through the open source movement. It was a huge catalyst. You had Adrian Boyer's ReapRap project, started around 2004. Their goal was amazing: Design printers that could actually print most of their own parts.
Self-replicating printers.
Yeah, about 70% of their own parts. It showed the potential for self-replication and dramatically lower costs. And then the Fab at Home project in 2006 aimed for similar low-cost open-source fabrication for everyone.
Those sound like crucial steps. But the real game changer for accessibility, the true inflection point, that came in 2009, right? What happened then?
That's when the key patents for the FDM printing process Scott Crumb's Stratasys patents expired. And that just opened the floodgates. Suddenly, a whole new wave of startups could jump in and build on that FDM technology. It led to this boom in commercial FDM 3D printers becoming far more accessible to the public. It really ushered in a new era.
And that leads us right into the 2010s and 2020s, a period of, well, mainstream adoption and absolutely incredible innovation. By the 2010s, metal end-use parts, actual functional parts, not just prototypes, began to be grown by additive manufacturing. You mentioned it really took off, especially in aviation. Can you give us a concrete example of that impact?
Absolutely. It's a perfect case study. Take GE's LAP jet engine. It now integrates 3D printed fuel nozzles, the original design for that nozzle, 20 separate parts that had to be assembled. With 3D printing, they condensed it into just one single part.
Oh, 20 parts down to one.
Yeah. And that didn't just simplify assembly, it also achieved a 25% weight reduction, which, for an aircraft, translates directly into fuel efficiency and reduced emissions. It's a massive win.
That's incredible. It's not just about efficiency then, it's about pushing the boundaries of what's even designable. You can create these internal geometries that were impossible with traditional methods, leading to lighter, more fuel-efficient, maybe even safer parts.
Yeah.
And this accessibility just kept growing, right? The prices kept dropping.
Oh yeah, the price continued to plummet. While commercial printers were still over $2,000, maybe, in 2014, by 2020 you could find decent quality FDM printers for less than US $200. That made 3D printing genuinely accessible to most people, hobbyists, schools, almost everyone.
And the breakthroughs just keep coming thick and fast now. In 2021, the world's first fully 3D printed prosthetic eye was given to a patient in the UK. That's amazing. Just this year, 2024, the world's largest 3D printer was unveiled at the University of Maine. It's, 96 feet long?
96 feet. It can print enormous things like molds for boat hulls or even small building structures. It's huge. And we've also seen AI-designed synthetic bone with record shock absorption also this year. And just in July, 3D-printed artificial blood vessels were developed that are as strong as natural ones. This is truly a technology accelerating at an incredible pace, pushing the boundaries of engineering, materials science, even biology.
Okay, so beyond the sheer cool factor and this rapid pace of innovation, what are the sort of unseen benefits? What makes 3D printing such a profound game changer? Why is it so transformative?
Well, it goes far beyond just replicating traditional manufacturing methods. 3D printing offers unparalleled design freedom. Designers aren't constrained by old rules. Think about individualization, creating custom-fit products easily. Prosthetics, tools, anything. It enables decentralization of production. You don't necessarily need a huge factory anymore. You could print things closer to where they're needed. And critically, it allows for processes and shapes that were simply impossible before.
That's right. And for businesses, it's a huge win for efficiency and customization. It dramatically speeds up prototyping, going from a digital concept to a physical object you can hold much, much faster. It can reduce manufacturing costs, especially for complex, low-volume parts. And it enables a level of product customization that's just not feasible with traditional mass production, often while improving product quality, too.
And its capabilities extend into entirely new frontiers. We're talking lightweight construction for vehicles and aerospace, which saves fuel. Critical repairs and maintenance, printing spare parts on demand, highly personalized prosthetics, as we mentioned, and even bioprinting for medical applications like tissues and eventually maybe organs. That's the holy grail for some researchers.
You're showing up everywhere.
Yeah, it's making inroads in the food industry, believe it or not. Rocket building, printing complex engine parts, design and art, obviously. It can even be used to produce components for renewable energy systems, like custom battery casings or parts for wind turbines. The versatility is just astounding.
What's also incredibly impressive, you mentioned earlier, is its precision and its potential for waste reduction. How does it achieve that?
Well, it can produce highly complex geometries with incredible precision and accuracy that's particularly valuable in fields like microwave engineering, where the exact shape is absolutely crucial for function. And because additive manufacturing only adds material precisely where it's needed, layer by layer, it generates minimal waste compared to traditional subtractive methods that start with a block and cut away everything you don't need.
Right, carving away material is inherently wasteful.
Exactly. So AM dramatically reduces material costs, the environmental impact of that waste, energy consumption, and ultimately our overall carbon footprint. It's just a much leaner way to make things in many cases.
Okay, so we understand why the benefits are huge.
Yeah.
How does all this magic actually happen? Let's talk about the general principles behind bringing a 3D idea into physical reality. Where does it start?
It all starts with modeling. You need a digital blueprint. Your 3D printable model is typically created using computer-aided design or CAD software. That's the most common way. You can also use 3D scanners or photogrammetry to capture existing objects and turn them into digital models. But CAD models generally lead to cleaner, more accurate prints with fewer errors because you're designing it digitally from the ground up.
Okay, so you have your digital model, then it needs to be saved in a specific file format the printer can understand. The most common one is STL, right? Stereolithography format. What is that exactly?
Right, STL is the workhorse. It represents the object surface using triangulations, basically. It covers the surface in a mesh of tiny triangles. It's simple, widely supported, but for really complex parts with lots of curves, an STL file can become enormous and a bit clunky.
So there are newer formats too.
Yeah, that's where AMF, the additive manufacturing file format, comes in. It was introduced around 2011. It uses curved triangulations, which helps manage those large file sizes better for intricate designs, more efficient. And importantly, before you print, any digital file needs a quick check for errors, like are there holes in the mesh? Do parts overlap incorrectly? These need to be repaired digitally to ensure a clean, successful print. This is especially true for models that came from 3D scans.
Gotcha. Check and repair the file. And here's where the literal layers come in, the crucial step of slicing. What happens then?
Right, slicing is key. A software program, logically called a slicer, takes your repaired 3D model. It digitally cuts the object into a series of incredibly thin, horizontal, two-dimensional layers, like a stack of paper printouts. This software then generates something called G-code. G-code is essentially a set of highly specific instructions tailored for your particular 3D printer model. It tells the printer exactly where to move its print head, how much material to extrude, the temperature, the speed, everything it needs to know to build that object layer by layer.
And the quality of your print depends heavily on the resolution, right? What does that mean in 3D printing terms?
Exactly. Printer resolution refers to a couple of things. First, the layer thickness, how thin each slice is. Typical layer thickness might be around 100 micrometers, which is about the width of a human hair. But some high-end machines can print layers as thin as 16 micrometers. That allows for astonishingly fine detail. The other part is the XY resolution, which is how finely the printer can move across the print bed horizontally.
Okay, so finer layers and finer XY movement mean more detail. What about how long it takes?
Well, build time varies hugely, obviously. A small, simple object might print quickly. A large, complex one takes longer. But compared to traditional manufacturing methods, especially for prototypes or custom parts, which could take days or months, additive systems can often reduce this to mere hours. It depends on the object's complexity and size and the specific printing process, but it's generally much faster for one-offs or small batches.
Okay, so that covers the basics from digital file to printed object. But the process doesn't necessarily stop when the printer finishes, right? There's often post-processing involved, and the variety of actual printing processes is truly astounding. Let's talk finishing first.
That's right. Getting the print off the machine is often just the start. Finishing can involve quite a bit. Common steps include sanding or bead blasting to get smoother surfaces, especially if you need a really polished look or feel. 3D prints often have visible layer lines, and finishing helps remove those. For some plastics, like ABS, you can even use chemical vapor processes. Acetone vapor, for example, can smooth the surface quite effectively by slightly melting the outermost layer.
Interesting. And I've heard about annealing as a post-processing step. What does that do?
Annealing is basically a heat treatment, like you might do with metal or glass. For 3D printed parts, particularly certain plastics, it helps improve the bonding between the layers and can enhance the overall mechanical properties, making the part stronger and more durable. You just have to be careful during the process, because it can sometimes cause the part to warp slightly.
And sometimes you combine printing with traditional methods.
Yeah, that's called additive or subtractive hybrid manufacturing, or ASHM. Pretty neat concept. You might 3D print a complex shape that's close to final form, then use traditional CNC machining to finish critical surfaces with very high precision and accuracy. It combines the best of both worlds.
What about that stair-stepping effect you sometimes see on curved surfaces because of the flat layers?
Right, that's inherent in layer-based manufacturing, but it can be minimized. Some advanced slicers support variable layer heights, where the printer uses thinner layers on shallow curves and thicker layers on steep vertical sections. That helps smooth things out. And of course, parts can always be painted. Although some multi-material printers can actually print in multiple colors right from the start, which is cool.
And one last thing about finishing supports.
Ah, yes, supports. Crucial, but sometimes annoying. If your design has overhanging features, the printer needs to build temporary support structures underneath them as it prints. These supports then have to be carefully removed after the print is done, either snapped off, cut away, or sometimes dissolved if they're made of a special soluble material.
Okay, makes sense. Now, materials, you mentioned it started with polymers, but now it handles metals, chocolates, ceramics, diverse range. I heard the earliest patented material was actually a hot melt metal alloy. For the personal printers most people might have at home, what are the common plastics?
Yeah, for those desktop FDM printers, the two most common polymers you'll see are PLA polylactic acid, which is popular because it's relatively easy to print and derived from renewable resources like cornstarch. And the other big one is PETG, which is basically a modified version of the plastic used in water bottles. It's a bit more durable and temperature resistant than PLA, but the really cutting edge stuff is in multi-material 3D printing.
Right, you mentioned that. Tell me more. How does that work?
It allows for creating these complex, heterogeneous arrangements of different materials within a single printed object. The software lets you specify the material properties for each tiny little volume element, or voxel, think of it as a 3D pixel. So instead of just printing a solid block of one material, you can design a part where, say, one section is rigid and strong, and it transitions smoothly into a section that's soft and flexible, all printed in one go.
So you could print like a tool with a hard metal tip and a soft rubber grip, all as one piece.
Exactly. That's the kind of capability it unlocks. It gives designers incredible control over material properties spatially. And this opens doors for really cool innovations, like 3D printed pills that combine multiple medications with different release profiles in one tablet. That could potentially decrease risks for patients by delivering precise, tailored dosages automatically.
That's amazing potential. And then there's the truly futuristic sounding 4D printing. What on earth is that?
Yeah, 4D printing adds the dimension of time to 3D printing. The idea is that the printed object isn't static. It's designed to change its shape or its function over time, usually in response to some external stimulus like temperature, light, or moisture. It allows for creating dynamic structures, things that can self-assemble or change rigidity on command.
Like a flat sheet that folds itself into a box when you heat it.
Sort of, yeah. Or materials that change their porosity. It could lead to entirely new classes of smart materials and devices. But it's still very much in the research phase. It requires significant advancements in controlling the material's microstructure during printing and developing specialized software to design these transformations.
Okay, mind slightly blown by 4D printing. Now, you mentioned earlier there are 7 main categories of additive manufacturing processes defined by ISO and ASTM standards. We obviously can't dive deep into every single one, but what are some of the key families, the main types of 3D printing processes our listeners are most likely to encounter or hear about? What makes them distinct?
Great question. It helps to group them. You broadly have processes based on material extrusion, like the common FDM printers squeezing out melted plastic filament. Then there's vat photopolymerization, which uses light, usually UV light, to selectively cure liquid resin into a solid. And another big category is powder bed fusion, where you use a high-power energy source, like a laser or an electron beam, to melt and fuse fine powders together layer by layer. Think of them as different tools for different jobs. Each excels in certain areas: materials, resolution, speed, strength.
That's a helpful breakdown. Can you quickly give us a sense of what each of those 3 main types is best suited for? Let's start with material extrusion, FDM.
Okay. Material extrusion, like FDM or FFF, fused filament fabrication, is the most common, especially for consumers and schools. It's great for rapid prototyping, making household gadgets, educational models, jigs and fixtures. Usually uses thermoplastics like PLA or ABS or PTG. Newer variants, like fused particle fabrication, FPF, are interesting because they can use plastic pellets directly, even from recycled sources like milk bottles, which is great for sustainability and cost.
Okay, versatile and accessible. What about powder bed fusion? That sounds more industrial.
It generally is, yeah. Techniques like selective laser sintering, SLS, which fuses polymer powders, or selective laser melting, SLM, and electron beam melting, EBM, which melt metal powders. This is where you get incredibly strong, high-resolution, geometrically complex parts, often made from metals like titanium or aluminum or high-performance polymers. It's perfect for demanding applications like aerospace components, medical implants, or intricate tooling. It's a very high-precision, high-strength method.
Right, so metal parts for jet engines, that kind of thing. And the third major one, vat photopolymerization.
This family includes methods like stereolithography, SLA, which was the first commercialized process, and digital light processing, DLP. They work by curing liquid photopolymer resins with UV light. These systems can create incredibly tiny features, sometimes sub-micron, and produce parts with very smooth surface finishes and intricate details. So they're great for things like highly detailed visual prototypes, jewelry casting patterns, dental molds and aligners, or microfluidic devices.
Fascinating how diverse they are, even within those main groups. And beyond these three, there are others, right? You mentioned binder jetting.
Yes, binder jetting is interesting. It works by depositing a liquid binding agent, like a glue, onto thin layers of powder, which can be sand, metal, or ceramic. The binder holds the powder together in the shape of the layer. After printing, you often have what's called a green part. Think of it like an unfired clay pot. It holds its shape but isn't very strong yet. It usually needs post-processing, like curing or sintering in an oven, to achieve final strength. A key advantage is that it can produce full-color prototypes by using colored binders, and it can be used for large parts, like sand cores and molds for metal casting.
Okay, and what about CAL, computed axial lithography? That sounds different.
It is different. CAL is a newer volumetric method. Instead of building layer by layer, it creates the entire object at once. It does this by projecting a series of 2D images, like a movie, from different angles into a rotating cylinder of photocurable resin. Where the light intensity exceeds a certain threshold, the resin solidifies simultaneously. It can be much, much faster than layer-based methods for certain geometries, and it can even print around existing objects, essentially embedding them within the print, which is pretty unique.
Oh, wow, okay. And LAM, liquid additive manufacturing.
LAM is specifically designed for depositing high-viscosity liquid materials like silicone rubber or other elastomers. The material is extruded and then typically vulcanized, usually by heat, to solidify it. It's great for making flexible, rubbery parts.
And DED, directed energy deposition.
DED uses a focused energy source again, typically a high-power laser or an electron beam, to melt material as it's being deposited. The material is usually fed in the form of metal powder or wire directly into the melt pool created by the beam. This isn't just for building new parts from scratch. It's increasingly used for adding features to existing parts or for repairing high-value components like turbine blades. Even conventional welding processes like gas metal arc welding can be adapted for DED.
So you could repair a worn-out metal part instead of replacing it entirely.
Exactly. Huge potential for maintenance and repair in industries like aerospace or defense. And just to round it out, there's even cryogenic 3D printing, which forms solid structures by precisely depositing and freezing liquid materials as they land, requiring a carefully controlled cold environment. It's still quite specialized, but shows the range of possibilities.
It's an incredible toolkit. So with all these different processes and materials, where are you actually seeing 3D printing making a difference today? The applications are incredibly diverse and seem to touch almost every part of our lives now. Which ones truly stand out to you as revolutionary? Where does it change the game in a way nothing else really could?
That's a tough one because there are so many. But for me, if I had to pick one area where the impact is truly profound and unique, it's probably personalized medicine. Things like custom prosthetics that fit perfectly, patient-specific surgical guides, dental aligners, hearing aids, and looking forward, the potential of bioprinting. Imagine printing replacement tissues or eventually even complex organs specifically tailored for your body, maybe even built using your own cells to avoid rejection. That's not science fiction anymore. Labs are actively working on this.
That's a truly profound shift. And it goes beyond just replacement parts, right, into surgery itself.
Absolutely. Surgical use has actually started way back in the mid-1990s. Initially, it was mostly anatomical modeling, printing a copy of a patient's bone structure, for example, so surgeons could plan complex reconstructive surgeries beforehand. That evolved into personalized implants designed specifically for that patient. And now, virtual planning combined with 3D printed surgical guides and instruments is used in things like joint replacement surgery and complex facial reconstruction. There have even been cases of 3D printed bioresorbable tracheal splints used to save newborns with breathing problems.
Wow. And orthopedic implants.
Increasingly used there, too. 3D printing allows for creating implants with porous structures, kind of like natural bone, which can help the patient's own bone grow into the implant for better integration and stability. The hearing aid and dental industries were early adopters and are now huge users of 3D printing for custom shells and aligners. And in pharmaceuticals, as I mentioned, it's enabling novel drug formulations. Personalized dosage forms tailored to individual patient needs may be combining multiple drugs or having specific release profiles. Some people expect 3D printers to eventually be common in hospitals and pharmacies for on-demand drug production.
And we even saw it play a role during the pandemic.
We did. During the early days of COVID-19, when supply chains for personal protective equipment were strained, 3D printers were crucial. Volunteers and maker communities around the world started printing face shield frames and other essential items to supplement the supply for healthcare workers. It highlighted the power of distributed manufacturing.
That's a truly powerful impact. Okay, beyond medicine, what other areas are seeing a radical transformation thanks to 3D printing?
Transportation is definitely a huge one. It's really taken off in the design and production of cars, trucks, and especially aircraft. We talked about GE using it for turbine parts. The Koenigsegg 1.1 supercar uses several 3D printed components for lightweighting and performance. There was a car called the Irby, which was notable for having a 3D printed body and windows maybe more of a concept, but it showed the potential. And Airbus's A350 XWB aircraft reportedly includes over 1,000 3D printed components.
1,000 parts on one plane model. That's significant.
It is. It's often for non-critical components like brackets or ducting, but it adds up in terms of weight savings and design flexibility. And remember that GE Aviation helicopter engine example, reducing the part count from 900 down to just 16. That's just astonishing for an industry where complexity and weight are everything.
And the military is using it too, you mentioned.
Yes, for parts in jets like the Eurofighter Typhoon and for printing spare parts on demand for the Israeli Air Force, it highlights how critical this can be for rapid repair, logistics, and getting custom parts quickly in demanding, often remote environments.
Okay, aerospace and automotive are big. What about some more surprising applications? You mentioned food earlier.
How about food? Yeah. It's definitely experimental for the most part, but people are using modified 3D printers to squeeze out food materials layer by layer. Things like intricate chocolate designs, custom candy shapes, decorative pasta, even simple pizza bases. NASA is exploring it seriously as a way to limit food waste on long missions and create tailored, nutrient-specific meals for astronauts. And one bioengineer even developed a method for creating fibrous plant-based meat substitutes using a 3D bioprinter to mimic muscle texture.
Plant-based steak from a printer. That's wild. And fashion.
Fashion designers are definitely experimenting. We've seen 3D printed bikinis, shoes with complex lattice structures, even entire dresses. Nike has used it extensively for prototyping football shoe designs, getting physical models much faster. New Balance uses it for creating custom-fit midsoles for athletic shoes based on runner data. And you can now even get consumer-grade eyewear frames printed, sometimes customized to your facial measurements.
Another fascinating area you mentioned is cultural heritage. How is it being used there?
It's being used for preservation, restoration, and importantly, dissemination. Museums are using 3D scanning and printing to recreate missing pieces of ancient relics or to make replicas of fragile artifacts for handling or display. They've used it to reconstruct parts of archaeological monuments, like structures at Tiwanaku in Bolivia. Some museums even sell or give away the digital 3D models of artifacts in their collections, allowing people to print them at home. It brings history to life in a new way.
And artists are using it too.
Yes, artist Moresha Nalahari has a powerful project where she uses 3D printing for feminist activism by researching and digitally reconstructing cultural artifacts and treasures that were destroyed by ISIS, preserving their memory digitally and physically.
That's incredible. Architectural replication is another big one visually. That steel bridge in Amsterdam sounds amazing.
Right. It really is a feat of engineering. The world's first 3D printed steel bridge, unveiled in 2021. It spans 12 meters across the canal. It was created by robotic arms equipped with welding gear, essentially printing layers of stainless steel over 4,500 kilograms of it over a period of 6 months. It shows the potential for large-scale construction.
And even circuit boards, how does that work?
Yeah, 3D printing can streamline the manufacturing of printed circuit boards, PCBs. Traditional PCB making involves multiple steps like imaging, drilling, plating, etching. 3D printing can potentially reduce these. It uses special conductive inks, often polymer-based with silver particles, to print the conductive traces and insulating layers directly, building up the circuit layer by layer. This can significantly cut production time, especially for complex, multi-layered board designs or prototypes. And beyond all these industrial uses, let's not forget education and communities. 3D printing, especially with affordable open-source printers, is increasingly entering classrooms. It's great for teaching design thinking, rapid prototyping, and even for fabricating low-cost, high-quality scientific equipment, leading to what some call open-source labs. Many public libraries now also house 3D printers, providing community access to the technology. The maker Naomi Wu considers its use in Chinese classrooms for teaching design principles and fostering creativity a really key development for the future.
And of course, the hobbyists. That explosion after the FDM patents expired.
Exactly. Since around 2005, and especially after 2009, it's been huge for hobbyists. People use it for artistic applications, creating custom miniatures for gaming, making practical household items like replacement knobs or custom organizers, even building complex things like working clocks or gear mechanisms. As of 2019, it was estimated that maybe 2 million people worldwide had purchased a 3D printer for hobby use. It's a massive community now.
So with all this innovation and accessibility, especially with millions of people potentially printing things at home, the legal landscape must be trying to catch up. When it comes to intellectual property IP, things like patents, copyrights, trademarks, they might all apply.
Yeah.
What are the key issues people need to be aware of?
It's definitely a complex and evolving area. It's still somewhat unclear how existing IP laws will apply effectively if 3D printers become truly mainstream for personal or nonprofit use. Generally speaking, if an object you want to print is protected by active intellectual property, like a patent on its design or function, or copyright on its artistic expression, you would likely need a license from the rights holder to legally print it, especially for commercial purposes. Though, depending on the country and the specific situation, there might be exceptions for private or non-commercial use.
Okay, so patents cover the invention itself, the process, the machine, or a functional design, and they typically last about 20 years. Printing, using, or selling a patented item without permission could lead to infringement. Copyright is different, right? It covers the creative expression fixed in a tangible medium like a sculpture, a character model, or even the digital design file itself. That usually lasts much longer, often the author's life plus 70 years.
Exactly. And an important distinction, particularly in U.S. courts, is the idea of functional versus expressive features. Courts often rule that a feature of an object isn't protected by copyright if its shape is dictated purely by its function, unless that expressive element can be conceptually separated from the functional aspects. But how this applies to complex 3D models can be tricky, and international laws differ, which adds another layer of complexity if you're sharing files globally.
Right. Another area that generates a lot of headlines and legal debate is firearms. The U.S. Department of Homeland Security has pointed out that easily accessible 3D printable firearm files pose public safety risks because they could bypass traditional gun control measures and are hard to trace.
And that's a major concern for regulators. Attempts have been made to ban the online distribution of these files or restrict the printing of firearms. However, realistically, completely preventing production this way is very difficult. Online file distribution is notoriously hard to control once something is out there. Some legislators have proposed regulations on the 3D printers themselves, like requiring them to be unable to print firearm components. But advocates against such measures argue this would be futile, technically difficult, would harm the legitimate 3D printing industry, and could infringe on free speech rights regarding the distribution of information.
It's a really contentious issue, and internationally.
Internationally, where gun controls are generally much stricter than in the U.S., the ability to print firearms might be felt even more strongly, potentially undermining existing regulations in new ways.
Okay, moving away from firearms to aerospace, that's another highly regulated industry. How are bodies like the FAA handling 3D printed parts?
Right. In the U.S., the Federal Aviation Administration, FAA, is actively involved. They have to be, because all parts used on certified aircraft must meet stringent safety and performance standards and be FAA approved. They've been developing specific guidance and qualification processes for additive manufacturing techniques used in aircraft parts. It was a significant milestone back in 2016 when the FAA approved that 3D printed fuel nozzle for the GE LE Pat engine we discussed. It showed that AM parts could meet the rigorous standards.
So quality assurance is paramount there. Are general standards emerging for industrial 3D printing?
Yes, absolutely. Ensuring quality and consistency is critical for building trust and enabling wider adoption, especially in demanding industries. International standards bodies like ISO and ASTM are collaborating to develop standards. Examples include ISO's TEMM 529000-21, which covers general principles and terminology, and ISO STMM 52920.2023, which defines specific requirements for industrial additive manufacturing processes and production sites to ensure quality control. These standards are crucial for maturing the industry.
Okay, that makes sense. Finally, let's zoom out and look at the bigger picture. The health, safety, and the broader societal and environmental impacts of this technology, starting with health and safety. If you have a 3D printer at home or work, what should you be aware of? Are there risks?
Yes, there are potential hazards to be aware of, especially with desktop polymer printers. When you heat polymer feedstock materials like PLA or ABS filaments, they can release ultrafine particles, UFPs, and volatile organic compounds, VOCs, into the air. Some studies have linked exposure to these emissions to respiratory and cardiovascular issues, so good ventilation in the printing area is really important. Using an enclosure, maybe with a filter, is often recommended.
Okay, air quality is one thing. What else?
Well, the extrusion nozzles on FFM printers get very hot, typically 190 to 260 degrees Celsius, or even higher for some materials. That's a significant burn hazard if you touch it accidentally. For vat photopolymerization printers, they often use high-powered lasers or UV light sources. These are usually enclosed during printing for safety, but care should be taken during maintenance. And like any machine with moving parts, there's always a small risk of minor mechanical injuries, like getting a finger pinched in the moving gantry. Also, the electrical safety features on some lower-cost desktop printers might be minimal, though the operating voltages are generally low.
What about noise? Are they loud?
Noise levels can vary quite a bit between printers. Some are very quiet, maybe 15 decibels, while others can be quite loud, up to 75 decibels or more. The main sources of noise are usually cooling fans, the stepper motors that move the print head, and sometimes the bearings. People use various methods to dampen the noise, like putting the printer on a vibration-isolating mat or building a soundproof enclosure around it. Research into all these potential hazards is ongoing, and agencies like the European Agency for Safety and Health at Work, EU OSHA, are publishing discussion papers to help understand the risks and promote safe practices.
Good to know. Now, thinking about the wider societal impact, how is 3D printing changing the way we make things and maybe even the structure of our economy?
It's definitely forcing manufacturing firms to think differently, to be more flexible and adaptable. Advocates have long predicted that 3D printing might help counter globalization by enabling more localized production, making things closer to the point of need. While that's happening to some extent currently, it seems AM is more often complementing traditional subtractive manufacturing methods rather than entirely replacing them, at least for mass production. It excels in customization, complexity, and low-volume runs.
But some see it as more revolutionary than that.
Oh, yes. Futurologist Jeremy Rifkin famously claimed that 3D printing signals the beginning of a third industrial revolution, shifting away from centralized mass production. It's certainly having a tangible impact in areas like humanitarian aid. The ability to do distributed manufacturing printing needed supplies like medical devices or repair parts directly in remote or disaster-stricken areas can reduce transportation costs, minimize waste, and potentially foster local production economies.
That's a powerful idea. How else might it change society?
Well, it could further blur the lines between home and workplace, as more design and production potentially happens outside traditional factories, maybe more flexible work arrangements. It could even reduce the need for some high-speed freight services if more goods are made locally on demand. And as we discussed, those big questions around copyright legislation and intellectual property will continue to evolve as the technology becomes more pervasive.
And you mentioned this connection to commons-based peer production. What does that mean in this context?
It refers to the idea that 3D printing, especially when combined with open source designs and collaborative online communities, enables a different kind of production model. Instead of relying solely on large corporations and economies of scale, making lots of identical things cheaply, you can move towards economies of scope where the value comes from sharing infrastructure, like printers or digital designs, to produce a wide variety of customized things efficiently. Think shared workshops, makerspaces, online design repositories. However, alongside these positive visions, there are concerns. We touched on easier weapons manufacturing. There are also worries about the recyclability of some specialized materials, especially nanomaterials, and the potential for easier counterfeiting of goods.
This sounds like it could really shake up the job market, too.
Yeah.
What are economists saying about the potential impact on labor?
They're definitely discussing it. Some prominent economists like Larry Summers and Michael Spence have raised concerns about the potential devastating consequences for labor, particularly for routine manual and cognitive tasks that can be automated or replaced by technologies like AI and 3D printing. It forces us to have difficult conversations about wealth distribution, the future of work, and the need for new economic growth models, perhaps built more around digital technologies, creativity, and human capital development rather than traditional manufacturing labor.
That connection to local production is interesting. Any recent examples?
Yeah, a nice small-scale example from just this year, 2024. A 3D printer was donated to the Juan Fernandez Women's Group in a remote island community off Chile. It's helping them fix broken equipment locally, things they previously had to wait months for imports to replace. It perfectly highlights that potential for localized problem-solving and production.
That's great. Finally, let's talk about the environmental impact. It seems like a mixed bag. Are 3D printers ultimately good or bad for the planet?
It's definitely complex, with both significant benefits and some drawbacks. On the plus side, the biggest win is waste reduction. Compared to most subtractive methods that carve away lots of material, additive manufacturing typically uses only the material needed for the part, plus some support structures. This drastically reduces material waste. Less waste means less raw material extraction, less energy used in material processing, and often a smaller overall carbon footprint for the part itself. Localized production, if it takes off, also reduces transportation distances and associated emissions.
And enabling repairs.
Yes, that's another key benefit. Allowing consumers or local repair shops to create replacement parts for appliances or equipment can extend product lifespans, fighting against planned obsolescence and reducing the need to buy entirely new products. Plus, 3D printing is a key enabler of lightweighting in vehicles and aircraft, creating strong but lighter parts, which directly saves fuel and reduces greenhouse gas emissions during operation.
Okay, so a lot of potential positives there. What are the main environmental downsides?
The main concerns are around the energy consumption during the printing process itself. Some processes, particularly those using high-power lasers or maintaining high temperatures for melting metal or polymers, can be quite energy-intensive per part produced, especially compared to efficient mass production methods like injection molding for very large volumes. Also, while material waste is reduced, some of the waste that is generated, like support structures, failed prints, or unused powder bed systems, can sometimes be difficult to recycle, especially mixtures of materials or in highly regulated industries where material traceability is paramount.
But I assume research and industry efforts are trying to address these drawbacks.
Absolutely. There's a lot of work being done. We mentioned some large FDM printers that can now accept recycled plastics, like shredded milk bottles or PET pellets, as feedstock. And there are active efforts to develop more energy-efficient printing processes and to improve the recyclability of common printing materials, including producing metal powders from recycled scrap metal. The push is definitely towards making additive manufacturing a more sustainable and integral part of a future circular economy.
Wow. We've really covered a lot of ground today. We've taken an incredible deep dive into the world of 3D printing, tracing it from its surprisingly early sci-fi imaginings and conceptual patents all the way to being a truly transformative force. It's touching practically everything from medicine and aerospace to fashion, food, construction, and even how hobbyists create things at home. It's clearly a technology that offers unparalleled design freedom and customization, while fundamentally rethinking manufacturing efficiency and waste.
It really is. And it's clear that the full impact of 3D printing is only just beginning to be understood. Its evolution is ongoing, and it will undoubtedly continue to reshape our world in ways we probably can't even fully predict yet.
So here's something to think about as we wrap up. Consider this. As 3D printing continues to evolve, as it becomes even more accessible, making creation increasingly localized, and as the range of usable materials becomes even more versatile, How will our fundamental relationship with things, with physical objects, change? Will we genuinely become a society of universal makers, repairing and producing more of what we need on demand, right where we need it? Could this drastically alter global supply chains and our very concept of ownership and consumption? And maybe most importantly, what skills will be the most valuable in a world where theoretically almost anything can be printed? What does it mean to be a creator or a consumer in that future?